Morning. I'd like to give you a lecture on explosions. So it's relating to the momentum topic, and this is 9.5 if you are following along from the AQA A-level textbook. So we're going to be looking at what are the energy changes that takes place in an explosion. What can be always said about the momentum of a system that's exploded, and what are the consequences if there are only two bodies that move apart after an explosion. Now, by a body, I don't sort of mean like you and me, kind of a body, we mean kind of like an object. So let's just carry on. Right, so what is an explosion when we're talking about it in a physics concept? So an explosion is when the initial momentum is zero and the two objects fly apart after initially being at rest. So I don't know, I'll just draw a circle and a square. This can be the initial, this could be the initial state, and then final state could be the circle. The circle would go that way and the square would be going that way. So two objects initially at rest and then they go in opposite directions. So from this we can say two things really. We can say that each object must have equal and opposite momentum. That's really, really important. Each object must have equal and opposite momentum. Well, how do we know this? Well, if it's initially zero and we know initial equals final, then that must be true, and I'll show you in a minute. And we also know that it must move in the opposite direction. And we know this just from conservation of momentum. Because momentum's a vector, you can't have two positive things add up to zero, essentially. So let me just show you why that's the case. So I'll take my square and my circle again, and we'll look at the momentum before. So we'll have call this the A shape, and we'll call this the B shape. So this has got mass of B, this is velocity of A, this is velocity of B, and this is the initial. And in the final state, we've got A going this way, and we've got B going this way, and that's still VA, and that's still MA. And this is VB, and this is MB. So we know from the last lecture that the sum of momentum before equals the sum of momentum after. So we have V, well, you know momentum is mv, so we have MAVA plus MBVB. I should have labelled these velocities to show that they're initial and final. So let me just go back and put these in. And that equals MAVA plus MBVB, where that's a final velocity. Now, good thing here, we know that both objects are initially at rest. So we know that VAI and BAI is 0, so that term is 0, that term is 0. which means that we have MAVAF must equal minus MBVBF, which essentially means that the momentum of this one here must be equal and opposite to this one here, because the momentum of the A shape is the mass of the A shape times the final velocity of the A shape, which is this here, and it must be equal to and just the opposite sign to this one. So that's the proof there that essentially that the momentum is equal to each other and opposite in direction. So that's proof of these two statements here. And they must move off in the opposite direction as well. Because if they don't, this relationship would not hold. Because if you remember from the wall problem last time, if there's a collision, it's at the angle theta. So if you had, I don't know, the circle and the square, but the square moved off this way and the circle moved off that way, the momentum wouldn't be equal and opposite, because it would have to take the parallel component here. So it just wouldn't work. So they would have to go off in opposite directions. So that is a fairly complicated way of quite a basic proof. Let's just show you how this works. So got a gun, mass 2.5 kilograms, and has a recoil velocity of 8 meters per second. What is the velocity of the bullet if it has a mass of 0.02 kilograms? So I always draw out my initial first. Gun, bullet, final. Gun, bullet, going that way. Now, initially we know it's at rest, so we know initial momentum is 0. Final momentum. The gun is going back this way. The gun has a mass of 2.5 kilograms. And it goes 8 meters per second. The bullet has a mass of 0.02, and we're trying to find its velocity. So we know that initial must equal final, so I'm going to do it in full, just so you can see the whole calculation. Initial momentum equals final, so our final. Now we need to be careful of our signs here, so I'm going to say that right is positive. So we're going to have our momentum of the gun is going to be minus 2.5 times 8, and then plus 0.02 V. Therefore, well, minus 2.5 times 8 is 20, and take it to the side, 20 equals 0.02 V. So 20 over 0.02 equals V, which is 1,000 meters per second, which is pretty quick. I mean, some of you could have just seen and gone, well, obviously you could have just gone, obviously this is an explosion problem, so the momentum of the gun must be equal and opposite to the momentum of the bullet. Therefore, momentum of the gun equals 2.5 times 8, which is 20, and that must be equal to the momentum of the bullet, 0.02 v, and then done it that way very quickly. And that's okay, because you knew it was an explosion. But I wanted to show you where it all comes from. Now let's talk a little bit about the energy conservation here. So there's a few ways that we can model explosions in the lab. I'm not going to fire a gun. What we could do is we can get these trucks with these springs on the end, kind of just here, and you push them together and then you let them go. Now this is quite a good model for conservation of energy, because the kinetic energy of the trolleys just after the release would be almost exactly equal to the energy that's stored in the springs used to compress them and push them together. Because we're obviously transforming energy from one form into another, because initially it rests, so we haven't got any kinetic energy at the start. So we've got to get it from another form to another. So here we've got elastic energy. If we're talking about a tank, and if we use something like gunpowder, we've got chemical. Now, if we're using chemical energy as our initial store, the kinetic energy of the objects due to the explosion is obviously going to be less than the initial energy, or than the initial chemical energy, because we're going to have things like sound, light, and heat given out as well, but there isn't too much of that in the trolley example. So if you're asked in an exam about energy transformations, just be aware what scenario your explosion is taking place in. So hopefully you are now in a place to answer the three questions at the bottom. What are the energy changes that take place in an explosion? Let's use a different colour. What can always be said about the momentum of a system that's exploded, so it's equal and opposite? And what are the consequences if only two bodies move apart after an explosion? Well, they have to go in the opposite directions. So I hope you've learned a bit about explosions. It's a GCSE topic, so hopefully it's not been too taxing for you. And that's